Mr. Tarrou, in this algebra lesson, we are going to be introducing how to extract roots and rewrite or simplify radicals. We're also going to be discussing how you rewrite a radical with a rational exponent, or put it into exponential form. Now, this is not the first time I have made lessons on this topic, so I'll put some links to other lessons in the description if you'd like to see more examples. But we're ultimately going to go through 6 examples after doing our initial page of notes. So the big sticking point with simplifying radicals is to realize that when you take an even root, there's a difference between that and taking an odd root. So we have here as a quick example to justify what we have written in orange. If you take -2 and you cube it, well, you get -8. -2 times -2 is +4, times -2 is -8. Now, when you take the cube root of -8, you get the answer of 2. We started with -2, and we end with -2. And yes, exponents and roots are inverse math operations. They they undo each other. So when you see this power of 3 and this index or root of 3, you can think of, well, they're just going to cancel each other out, and we're just going to be left with -2. But something curious happens when you deal with even roots. As we see here, we have -2 raised to the second power, and that -2, grab a different colored chalk here, -2 squared, now that is going to be equal to -4, because the power of 2 is only being applied on the base of 2, and the negative just sits out there and you get the answer of -4. But when you have -2 wrapped in a set of parentheses and it's squared, well, then that's going to be -2 times -2, which is +4. So -2 in those parentheses squared, +4. Now, when you take the square root of 4, well, it is technically true that when you take the even roots of a number, there's 2 answers, a positive and negative answer. Like, I can say, what's the square root of 4? And you can say 2 or -2, because -2 times -2 is +4, and +2 times +2 is +4. But in textbooks, when they give you a radical notation, if there's no plus or minus in front of that radical notation, then you're expected to only give the principal root, or the positive root. So the square root of 4 is going to be equal to 2. That means that we started with -2 and we ended with +2. So the power of 2 and the square root, they didn't exactly make the phone ring. So while the power of 2 and the second index there didn't make the phone ring, it did act as a set of absolute values. So we need to remember that, yes, powers and roots are inverse math operations. They kind of effectively cancel each other out. But if n is odd, you're going to get the exact same number that you see inside the radical. But if n is even, so not necessarily just a power of 2, but if n is even, then as you see here, we started with -2, we ended with +2, and really the absolute value should be in here. It acts as an absolute value symbol. It's going to give you that same number, but it's going to make it positive. So that'll be something we need to think about as we go through our 6 examples. Radicals in exponential form. Most people understand radicals like square roots and cube roots more than fractional exponents when they're outside of the math class and maybe forgotten some of the skills that they learned. But as you're simplifying radicals, really working with them in with their sort of rational or fractional exponent form is a lot easier. So we do like to know how to write a radical with a fractional exponent. And if there happens to be a power applied to the factors or the term, the one term that is inside the radical, that power is going to be on top, and then the index goes into the denominator. Now, this only works if x is greater than or equal to 0 when n is even, because if you think about taking, hopefully you can see the red on the camera, if you think about taking the square root of -4, there is no number. Is it 2? 2 times 2 is 4. No. Is it -2? -2 times -2 is also +4. So no. When you take an even root of a negative number, what you're going to get is something called an imaginary solution, that I. Now, if you've studied that, great, you know what I'm talking about, and if you haven't, that's okay too, because we're not talking about imaginary solutions in this lesson. So that's why we say that what you're taking the root of needs to be basically greater than or equal to 0. I can't just say positive because that leaves out 0. When n is even, when you're taking an even root, and this double r, if you're not sure what that notation is, all real numbers. The base can be any real number when n is odd, because see here we could take the third root of a negative, not odd. Well, the root's odd. So we can take a third root of a negative number and get a negative answer. Must be the cold medicine. So review of properties of powers. We're going to be using that a little bit in this. So let's remember that when you multiply like bases, you can write that as a single base instead of two individual bases by adding the exponents. A quotient rule of powers, when you divide with like bases, you can subtract those exponents. Power to power, something raised to a power, and then that expression raised to another power, you can bring that down. Now this is just a quick review. We're assuming you've already been taught this. I am. That's a to the m times n. If you need a review of properties of exponents, I'll include links to those lessons as well in the description. Product to power. Now, a lot of students, if there were like a plus or a minus between, two terms, a lot of students will like to, when they learn that power to power, to drop this exponent that's outside of the parentheses down on each of those exponents and write kind of effectively what we have here, a to the m times p and b to the n times p. Well, you can, there is a product to power, but there is not, sort of an addition to power. When you have two terms, say, and you raise it to a second power, you're going to get three terms, not the two. So this really, these two properties only work if you have one term inside that parentheses raised to another exponent. So this is going to be, as we said, you can bring this power down when there's multiplication there, a times m to the p, b times m, not to the p, but times p. Quotient to power, same thing. This is only one term. No, there's no addition or subtraction separating those terms. So a to the m to the p power and b to the n to the p power. Remember that anything to a 0 power is equal to 1. That can be explained, if you haven't had a teacher do that before, using the quotient rule. Something like this could be a to the m divided by a to the m. Well, when you divide like bases, you subtract those exponents. That's a to the m minus m. Well, that's a to the 0 power. Well, anything divided by itself is 1. Yeah. And when you divide like bases and subtract those exponents, you get an exponent of 0. So a to the 0 power is equal to 1. And the negative exponents, if you have a base raised to a negative exponent, you can make that exponent positive by moving the base either to the denominator, if it's already in the numerator, or if that base with the negative exponent's in the numerator, you can bring it up and move it into the numerator. And you can explain how this works with that quotient property as well, but I'm out of space, and I'm just trying to keep these lessons relatively short and not review everything at the same time. So we're going to move on to our 6 examples. If you look at some other lessons, I'll explain how that last one works as well. But let's go to our 6 examples right now. Bam! So here we have our 7 examples. I misspoke earlier. I thought there were 6. So we're going to rewrite each expression using rational exponents for our first 2. So as we look over here in problem number 1, the y, it's not written, but it has a power of 1. And when you don't have an index on the top left-hand corner of your radical notation, that is an index of 2. So we're taking the square root of x to the 5th times y to the 1st. All right. So it doesn't say to simplify this, it just says to rewrite the expression using rational exponents. So this is just simply going to be, well, the x has a power of 5, so it's going to be x to the 5. Now, we're taking the square root of x to the fifth. Ooh, you know what? I could just make one extra little line of work here and remind you that maybe hopefully you saw this when you were simplifying radicals, like taking the square root of 32. When you take the square root of 32, now I'm off on a tangent here, but nope. You can simplify this radical, make the number inside the radical smaller if there's a perfect square root inside a factor, which is a factor of 32. Well, 32, that's 2 times 16. And do you see what I just did there? When you take this number and factor it and say, well, it's 16 times 2, you can give each of those factors their own radical. And then you can simplify each of them separately. The square root of 16 is equal to 4, and you get 4 is square root of 2. So the square root of 32 can be rewritten or simplified down to a form of 4 times the square root of 2. You can do that with factors. You cannot do that with addition and subtraction. When you have multiple terms inside of your radical, sorry for the heat there coming on, you don't have that flexibility, and it's not as easy to work with those radicals. But with multiplication and division, you can. So this is the square root of x to the fifth times the square root of y to the first. And now I can just rewrite that with the power over index, x to the 5 over 2 times y to the 1/2. And that is, just strictly rewritten so that we're using rational exponents. Now I can continue to fiddle with this maybe and put it into other forms, like if this is our multiple choice test. Maybe, I don't think you would, I think you would see this as one of your multiple choice answers, but we could write this as, maybe instead of going into individual factors, say we have x to the fifth, y to the first, and then all of that has the square root being applied to it. So you can wrap that with a power of, with your root in the denominator as a power of 1/2. And then when we do power to power, that product to power, we can see that we can end up with the same answer. So that's all there is to that. And if it's a multiple choice question, maybe you need to write your answer in the form of one of the multiple choice questions. Just be confident in your skills and know maybe the format that you have is not, possibly the format of one of the answers. And I'm standing in front of the question. So over here, same thing. We can apply that third root now to each of these factors, and a division sign is kind of another form of multiplication. So we sort of, in a sense, have 3 factors there and give each of these 3 factors that third root, much like you just saw me here do with example number 1. And that's it. We have rewritten this radical notation into rational exponent form. Now, I'm going to do this later on here in these other problems where it says to actually simplify. What do you do when the numerator is greater than the denominator when you write these radicals in fractional form? Because it will simplify a little bit more than that, but that's strictly written now with rational exponents. You can take it a little bit farther. We'll do that here, especially with, like, say, well, actually all of these, but especially with 6 and 7. We're going to rewrite each expression using radicals now. Well, yeah, when you have fractional exponents, the top, or the numerator, for proper vocabulary, is the powers that's going to be left applied to each of these factors, and the denominator of your fractional exponents, again, are your root, or your index of that root, of that radical. So we're taking the second root of each of these factors. So that can be written as x to the first times y to the third, and that's all raised to the 1/2 power, kind of undoing that power. My textbooks I normally teach out of don't list that, what is it called? Product to a power and quotient to a power separately, like this textbook I'm making notes out of right now does. So I'm pausing on the name, but I just call that power to power. Excuse me about my throat here. Now I can take and go, oh, all of this has that applied to it, that 1/2 power, that square root basically. And there we have our expression with rational exponents written as a radical. Now things are going to get a little bit more interesting here with example number 4, because our our indexes or our roots are different. This is really where fractional exponents come in to be nice and easier to handle, because if I said to rewrite the cube root of r squared times the fifth root of d and say rewrite that with a single radical, in that format, that looks really confusing. A lot of students wouldn't get that correct. But here I can say, well, if you rewrite these two fractions, just think about if you were trying to add or subtract them, you would need a common denominator. Well, with fractional exponents, that common denominator is a common root or a common index. Oh, you can write them. If you have a common root or an index, then you can write that one singular radical notation. So if you were to add 1/3 plus 1/5, what would the common denominator need to be? What would be the lowest common multiple between 3 and 5? Well, 3, 6, 9, 12, 5 doesn't go into any of those, 15. Oh, 5 goes into 15. So the lowest common multiple between 3 and 5 is 15. So that means we're going to multiply this fraction by 5, and 5 over 5 is equal to 1. So we're just going to make it look different, not change its value. I'm effectively multiplying 1/3 by 1, because 5 divided by 5 is 1. And we turn a 15 and 5 into 15 by multiplying it by 3. So we're going to multiply the numerator and denominator by 3. Now we have r to the 5 over 15th power times d to the 3 over 15th power. Now, like we have up here with number 3, each of our factors have a common root or index of 15. So like I wrote here with that power, pull that power of 1/2 out, we can write r to the 5th, d to the 3rd raised to the 1/15th power. And I hear the phone ringing. And as we simplify these expressions, we need to start thinking about what we pointed out at the beginning of the notes. When you have even powers and you have even roots, that acts as an absolute value symbol, and you need to account for that in your work. And I think the simplest thing to do is to simply just blow this up as much as we can and see it in tiny little factors. So we have the square root of x squared times the square root of y to the 4th. Okay, now technically we've expanded that a little bit, giving each of those factors their own radical, but the note said something about the nth root of x or a variable or some base to an nth power. So the root and the index was the same before we started talking about whether we needed absolute value symbols or not. So let's expand this a little bit more and write the square root of x squared times the square root of y squared times the square root of y squared. So those inverse math operations, yeah. A power of 2 and a square root cancel out. Power of 2 and a square root cancel out. Power of 2 and a square root cancel out. But our index here is 2 and our power is 2. So that's going to act as an absolute value symbol. So we end up with the absolute value of x times the absolute value of y times the absolute value of y. Now, I can bring these together and say we have the absolute value of x times y, which is y squared, and write that as our answer. And your teacher may be accepting that as an answer because you have remembered that you accounted for the fact you needed to include those absolute value symbols when the power and the root were both even. But the point of the absolute value symbol is to make sure your answer is positive. Well, when you take any number and you raise it to an even power, like -3 squared is -3, excuse me, parentheses, -3 times -3 is +9. So this even power is going to guarantee that whatever you get from y squared is going to be positive. So actually, we don't need the absolute value symbols around the y squared because of that even power. And our final answer, just because I'm afraid I'm going to run out of room, comes out to be x, the absolute value of x, times y squared. Now here, it's going to be actually a little bit simpler. because our power and indexes are odd, so we're not going to have to worry about those absolute value symbols. And we're just going to take the fifth root of 32 and the fifth root of x to the seventh. Maybe you know what this is, maybe you don't, and you may not show your work in the same fashion I'm about to, but I want to, I erased the notes. Oh, I want to highlight maybe how you deal with the numerator, the power that's bigger than the root. So I'm going to write the fifth root of 32 is equal to 2. And really I'm pausing because there's two ways to think about how to work out this problem. Let's do it, let's keep it with radical notation. I can write this as the fifth root of x to the fifth times the fifth root of x to the second, right? Because x to the fifth times x to the second, when you multiply like bases, because you can't bring radicals together with addition and subtraction, but with multiplication and division you can, as you saw that I just separated it. X to the fifth times x squared is x to the seventh, so this is an equivalent expression to what we have right here. And this index, that's why we talked about the review of exponential properties. That fifth root and that fifth power are going to cancel out, and you end up with 2x times the fifth root of x squared. Now, if you wanted to go into fractional exponents, which is not a huge advantage for this type of problem, but I promise you in some math problems, fractional exponents are way better than radical notation. We can write this as, well again, 2, and then x to the 7 over 5th power. Well, that's going to be, can be rewritten again with the idea of, separating an addition of fractions. We can write that as 2x to the 5 over 5th power times x to the 2 over 5th power, right? Because when you multiply like bases, you would add those exponents to write sort of like a final answer. And 5 plus 2 is equal to 7, and you have that common denominator of 5. So even though maybe we get a little bit dependent on our calculators, understanding how to remember how to add, subtract, multiply, and divide fractions are still important for a full understanding of math as we move through our math career. And 5 divided by 5 is equal to 1. That almost looks like a power of 5 on that x. Okay? So then finally down here with our last example, we're taking the fourth root of this big old expression. So let's pick a different color just so it all stands out separately. And I'm going to go, instead of keeping it in radical notation, I'm going to go into fractional exponent form, just to give you a different look to these solutions. And we have, except for the 16, we have 16, the fourth root of 16, because that's going to come out to an even number, so I'm going to leave it in radical notation. We have x to the 12 over 4. We have y to the 4 over 4, and we have z to the 16 over 4, giving that index to each of these 4 factors, not 4 terms. And we get the fourth root of 16 is equal to 2. We get 12 divided by 4 is 3. We get 4 divided by 4 is 1. And z to the 16 divided by 4 is equal to 4. Now I've got to be cautious here because my index is even, not odd. So I can't take an even root of a negative number. So all of these would need to be wrapped in a set of parentheses. And when we have an even power, we're guaranteed that that expression would be positive. So the z to the fourth does not need a set of absolute value symbols around it, but the x to the third and the y does. Now if you don't like that look, those fractional exponents, let's keep it in radical form and again blow it up like we did The first example, this is our last example, so we're almost done. We have the fourth root of 16. We have the fourth root of x to the 12th power. We have the fourth root of y to the 4th. And the fourth root of z to the 16th. Now, if I want to do a full expansion and just really blow this up to make you see everything, okay, so a lot of writing, but x to the 4th times x to the 4th times x to the 4th is x to the 12th. Excuse me. At least you can't catch my cold over the internet. We have y to the 4th, and we have z to the 4th times z to the 4th is z to the 8th. Now we have z to the 12th. Now we have z to the 16th. So I've just expanded this expression out as much as possible. And look, each of these even root, even powers, even root, even power, each of these are going to require, like we showed in the first example, an absolute value sign. So we have 2 times the absolute value of x and let's be honest, this is annoying. But you're really seeing that matching index and power and reminding you that you're going to need those absolute value signs. But one more time, the absolute value sign is meant to make sure that that answer is positive, and z to the 4th, because of that even power, is guaranteed to be positive. So one last time, this can be written as 2 times z to the 4th times the absolute value of x to the 3rd times y. Hope that helps you understand our introduction of simplifying and rewriting radicals as fractional exponents. I'm Mr. Tarrou. Bam! Go do your homework.